Welcome to this comprehensive guide on C-sharp networking, designed specifically for beginners. In this video, we will demystify the core concepts of network communication within the C-sharp ecosystem, providing you with a solid foundation to build connected applications. Understanding networking is a fundamental skill for any modern developer. Networking in C-sharp is absolutely crucial for modern applications, enabling seamless communication between different machines, systems, and even devices across the internet. This capability allows for distributed computing, real-time data exchange, and the creation of interactive online experiences, making your applications far more dynamic and powerful. Throughout this guide, we'll explore three pivotal areas: C-sharp sockets for low-level control, REST APIs for web-based communication, and Unity netcode for game objects, specifically tailored for multiplayer game development. We'll provide a clear, step-by-step approach to understanding and implementing each of these essential networking concepts. First, let's dive into C-sharp sockets, which are the fundamental building blocks and endpoints for any direct network communication. Think of a socket as one end of a two-way communication link between two programs running on a network, allowing them to send and receive data directly. Sockets allow programs to communicate across a network, whether it's on the same machine or across the globe. The System.net sockets namespace in C-sharp provides all the necessary classes and methods to implement robust socket programming, giving you fine-grained control over data transmission. To set up a basic socket, you primarily use the socket class. When instantiating it, you specify crucial parameters such as the address family, like addressFamily.internetwork for IPv4, the socket type, such as socket type, stream for TCP, and the protocol type, typically protocol type, TCP. Binding the socket is a critical step that involves associating it with a local endpoint. This endpoint is defined by an IP endpoint object, which uniquely combines a specific IP address of your machine and a port number, effectively telling the network where your application is listening for connections. For server-side sockets, after binding, the listen method prepares the socket to actively accept incoming connection requests from clients. This method also allows you to specify a backlog parameter, which determines the maximum number of pending connections that can be queued before being accepted. Once a client attempts to connect, the accept method is called. This method then creates a brand new socket specifically for each successful incoming connection, allowing the server to maintain communication with multiple clients simultaneously without blocking the main listening socket. Data is efficiently sent and received over the established socket connection using the send and receive methods. These methods typically operate on byte arrays, facilitating the exchange of information, such as simple text messages or complex data structures, between the client and server applications. It is absolutely vital to always remember to explicitly close the socket with the close method once communication is complete or no longer needed. This action properly releases system resources, such as port numbers and memory, preventing resource leaks and ensuring efficient application performance. A helpful tip for responsive applications: utilize asynchronous methods like begin receive and end receive to prevent blocking the main thread. This is especially crucial in GUI applications, where blocking can lead to an unresponsive user interface, ensuring a smooth and fluid user experience. Always implement robust error handling mechanisms to gracefully manage common network errors and connection issues. This includes handling exceptions like socket exception for connection resets or timeouts, ensuring your application can recover or inform the user appropriately without crashing. Next, we delve into REST APIs, which are a cornerstone for modern web development and crucial for inter-system communication across diverse platforms. REST, or representational state transfer, defines a set of architectural principles for designing networked applications, making them scalable and interoperable. REST APIs enable communication using standard HTTP requests, leveraging methods like GET, POST, PUT, and DELETE, forming the backbone of many modern web services and mobile applications. This standardized approach allows different systems to interact seamlessly, regardless of their underlying technologies. To begin building a REST API, you'll start by creating a basic ASP.NET Core Web API project within Visual Studio. This provides a robust framework and all the necessary boilerplate code to quickly set up your API, allowing you to focus on your application's specific logic. You'll then define a model class, such as a product with properties like ID, name, and price, to represent the specific data your API will handle. These models act as blueprints for the data that will be sent and received, ensuring consistency and structure in your API responses. Next, create a controller class, which is decorated with the API controller attribute to manage incoming HTTP requests. This controller acts as the entry point for your API, routing requests to appropriate methods, and handling the business logic associated with each endpoint. Implement get endpoints using the HTTP get attribute to retrieve data. For instance, you can create methods to return a comprehensive list of all products or a single product by its unique ID, allowing clients to fetch specific resources from your API. Post endpoints, clearly marked with HTTP post, are specifically used to create new data resources on the server. These methods typically bind the incoming request body, which contains the new data, directly to your model object using the FromBody attribute, facilitating data submission. For updating existing data, you will implement put endpoints using the HTTP put attribute. Similar to post, these methods bind the request body to the model, but they are specifically designed to modify an existing resource, often identified by an ID in the URL path. Delete endpoints, designated with HTTP delete, are straightforwardly used to remove data resources from the server. These methods typically take an identifier, such as an ID, in the URL path to specify which particular resource should be permanently deleted from your system. After implementing your API, it's crucial to test your endpoints thoroughly using specialized tools like Postman or Swagger UI. These tools allow you to send various HTTP requests and inspect the responses, ensuring your API functions correctly and as expected under different scenarios. A valuable tip: always use clear and descriptive route names for your API endpoints. Well-named routes significantly improve readability for other developers and enhance the overall maintainability of your API, making it easier to understand and extend in the future. It's imperative to always implement proper error handling within your API and return appropriate HTTP status codes. For example, return 200 OK for success, 400 for not found if a resource doesn't exist, or 500 internal server error for unexpected issues, providing clear feedback to clients. Finally, let's explore Unity netcode for game objects, often abbreviated as NGO, which is Unity's robust and flexible solution specifically designed for creating engaging multiplayer games. This framework simplifies the complexities of network synchronization, allowing developers to focus more on game logic. To get started with Unity netcode, you'll begin by setting up a new Unity project. Then, you'll import the netcode for game objects package directly via the Unity Package Manager, which integrates all the necessary components and scripts into your project, preparing it for multiplayer development. The Network Manager component is the central orchestrator for managing all network connections and spawning networked objects within your Unity game. It handles the life cycle of network sessions, from starting as a host or client to managing the instantiation of game objects across the network. To make a game object network aware, you create a networked prefab, such as a player character or an item, by simply adding a network object component to it. This component marks the object for network synchronization, ensuring its state can be replicated across all connected clients. You can spawn networked objects at runtime using the network object spawn method, which must be called on the server. Once spawned by the server, the object is automatically synchronized to all connected clients, ensuring everyone sees the same game state and newly created entities. To keep game state consistent across all players, use network variable to synchronize variables like player health, position, or score across the network. Any changes to a network variable on the server are automatically replicated to all clients, maintaining a unified game world. Remote procedure calls, or RPCs, are essential for sending commands from clients to the server and vice versa, enabling interactive gameplay. They are used to handle player input, trigger game events, or execute specific logic on remote machines, ensuring synchronized actions in a multiplayer environment. To efficiently test your multiplayer functionality, Leverage the Multiplayer Play Mode package within the Unity editor. This powerful tool allows you to run multiple instances of your game simultaneously within the editor, simulating a real multiplayer environment for rapid iteration and debugging. A practical tip for learning Unity netcode: always start with simple projects to grasp the fundamental concepts and workflow. Gradually build up complexity as you become more comfortable, rather than attempting to tackle intricate multiplayer scenarios right from the beginning. Utilize asynchronous programming techniques extensively to prevent blocking the main thread, especially during network operations that can introduce latency. This ensures your application remains responsive and provides a smooth user experience, even when waiting for data over the network. Implement robust error handling throughout your networking code to gracefully manage network errors, connection issues, and unexpected exceptions. This proactive approach helps your application recover from failures, maintain stability, and provide meaningful feedback to users when problems arise. Always consider basic security measures like data encryption and authentication to protect sensitive information transmitted over the network. Implementing these safeguards helps prevent unauthorized access, data tampering, and ensures the integrity and confidentiality of your application's communications. Follow clean code principles and use meaningful, descriptive names for variables, methods, and classes. This practice significantly improves code readability, making it easier for you and other developers to understand, maintain, and extend your networking components in the long run. Thoroughly test your networking code in various scenarios to ensure it works correctly under different network conditions. This includes simulating high latency, packet loss, and unstable connections to identify and resolve potential issues before deployment, guaranteeing a robust application. Add clear and concise comments to explain complex code sections and provide comprehensive documentation for your networking components. Good comments and documentation are invaluable for understanding the logic, especially in intricate network interactions and for onboarding new team members. Optimize your networking code to minimize bandwidth usage and reduce latency for better performance, particularly in real-time applications like games. Techniques include data compression, efficient serialization, and sending only necessary updates to keep network traffic lean and responsive. Properly manage network resources, such as sockets and connections, to avoid leaks and ensure efficient system use. Always ensure connections are closed and resources are disposed of when no longer needed, preventing your application from consuming excessive system memory or network ports.
In summary, a solid understanding of C# sockets for low-level control, REST APIs for web communication, and Unity netcode for game objects is absolutely vital for building modern, robust networked applications and engaging multiplayer games. These three pillars form the foundation of C# networking.
We encourage you to continue practicing these concepts, experimenting with your own projects, and exploring further resources to deepen your knowledge and skills in C# networking. The world of connected applications is vast and constantly evolving, offering endless opportunities for innovation.